Hi everyone, this recorded lecture is for Hydraulic Engineering, class number 24, intended for the 10th of April 2014, a Thursday. We aren't having class today because I'm traveling down to Clemson to help develop the NCWS Fundamentals of Engineering exam for environmental. So we'll be back in class normal time, normal location next Tuesday. Let's look at a couple of announcements for this class. First of all, there is a quiz that you need to complete, and it's an online quiz. It is 20-minute time limit. You can use your book, you can use your notes, but you should work through that quiz individually. That quiz is accessible on MU Online, and it will be open until 11:30 p.m. on Saturday, April 11th. So that should give you plenty of time to take that quiz. There's only one question. It may be helpful if you have a calculator, pencil, and paper handy when you begin so that you don't waste time scrambling for materials once the 20-minute clock starts. So go ahead and give that a try, that online quiz. And also homework number 11, the problems you can see there, including the lab demo that we did in class on Tuesday, which was Hydraulic Jump Day. That homework assignment is due on Tuesday, April 15th. And so if you have any questions with that, you can email them to me, and I'll do my best to respond via email, or of course you're welcome to stop by my office on Monday the 14th. I don't have office hours, but I should be in for most of the day, so feel free to pop in if you've got any questions. Today's class is on underflow gates, and it's related to hydraulic jumps, as you saw in the lab on Tuesday. It was an underflow gate that we used to cause supercritical flow in order to induce the hydraulic jump, and so this follows really nicely with what we've seen so far. I'll just mention at the beginning of this lecture that portions of it have been pre-recorded in a previous semester, and so there may be one or two references to yesterday or the last class period that don't necessarily line up, but all of the concepts and materials do line up, and so does the pencast examples that I've edited into this lecture as well.
We're talking about gates today. Do we need another copy of the notes? Do we have enough? We're all good? All right. So this is the most basic form of an underflow gate, and you can see from the handle on top, this kind of a gate would maybe be used by a farmer in a relatively low flow rate situation, and the way that you know that it would be relatively low flow rates is because it would be difficult to lift a gate like that because of the hydrostatic pressures if there was a very significant depth of water pressing on the gate. You can see that it's basically just a sheet of metal in between a frame, kind of like a window frame, where the water is going to be pressing towards us, and it would be holding the gate up against the surface along the edges. And so not only have you got the weight of the water to lift up when a gate like this is open, but also there's the hydrostatic forces pressing the gate up against the frame. So it'd be very difficult to pull that up if there was very deep water. And for that reason, when gates get to be much larger than that, there would be some sort of a crank on the top, oftentimes an electric motor to try and lift the gate. And this is a very substantial gate. These Waterman is sort of the dominant player in making underflow gates, and it's amazing once somebody dominates the market like this how sometimes difficult it is to get a gate for a project that you're working on. When I was a design engineer earlier in my career, I had designed water inflow to an irrigation canal and wanted just a pretty standard gate. It was about 3 feet by 3 feet, and the lead time on that was about 7 months for them to fill the order. So that's something that shocked me, is you'd think that there'd be a warehouse full of things like this, but they were made to order each one of them, and it took a long time to get it to the customer.
Why is it they're the only player?
I don't know. Low prices, great service. No, I'm not sure what it is, but Waterman, they certainly seem to have a stranglehold on the market. That was a number of years ago. It may not be the case any longer, but this is a flow equalization basin at a wastewater treatment plant. And you can see that there are a number of different gates here at different elevations. And the purpose for that is that depending on how much water is inside of the wet well, they want to be able to direct water to different places. There are other bypasses, and in fact, they're not pictured there is a sort of an overflow spillway where they could discharge wastewater directly to a stream if the water levels got too high. So gates are used to control flow rather than measure flow. And this is an example of a gate in the Netherlands that I'll just dim the lights a bit to make it a little bit more clear. Rather than having a flat surface, this gate has a curved surface, you can see. And it actually pivots about a radius, and the purpose for that is that it makes it easier to lift and lower the gate because the hydrostatic forces push through the center of rotation rather than in any of these flat gates, the water is actually going to be pressing the gate up against the frame and increasing the difficulty of opening it. That is avoided when you have a curved surface because the hydrostatic forces will just go through the center of rotation. And so now all you have to lift in a case like this is the weight of the gate rather than also having to contend with the hydrostatic forces that might otherwise press it closed. If we want to quantify how much water can flow underneath the gate, we can start by taking a look at the energy equation. And it's the same specific energy relationships that we've used in several cases already. The upflow energy, the upstream energy is equal to the downstream energy. Now here there are a couple of different elevations that are illustrated. The elevation 1 is referring to the headwater. There's the height that the gate is open, and then you can see that the water continues to contract after it exits the gate. And that's because the water is still accelerating as it exits the gate. And once it has stopped accelerating and reaches temporary equilibrium here at location 2, you can see that the depth is some coefficient of contraction, C sub C means coefficient of contraction, multiplied by the depth of the gate. And so if we want to, at location 2, equate how much energy there is, you can see that there's going to be a lot more velocity head than there was at location 1, where presumably we have supercritical conditions coming out of this gate and subcritical upstream of the gate, but not necessarily. It is possible that this was already supercritical. So the energy at 1 is equal to the energy at 2. And if we rearrange that expression, we can calculate the flow per unit width for this channel or a rectangular gate in terms of the two depths, the upstream depth y1 and the downstream depth after contraction y2. So the flow per unit width. We can quantify the discharge through the gate. The coefficient of contraction usually varies from 0.59 to 0.62. And here are a couple of different illustrations of rectangular gate and that curved gate that comes from the earlier photo. Here, one difference from the earlier figure is that Y sub G is used in some text to identify the depth of the gate, whereas here it's W. And these are taken from your text. W is the depth of flow underneath the gate. One of the problems with the weir that quantifies flow is that, of course, the sedimentation and accumulation of debris upstream of the weir. And so an underflow gate, as has been mentioned before, avoids that problem. And also, there's a relatively low amount of energy loss through an underflow gate. The coefficient of discharge is what accounts for the difference between the ideal flow conditions, which would occur if there was no energy loss, and the actual flow conditions. The coefficient of discharge can be estimated as a function of partly the coefficient of contraction, and then also it's partly a function of the difference in elevations between the upstream depth and downstream. So if we know the two depths, the downstream depth and the upstream depth, then we can calculate the coefficient of discharge. So I'd like you to get some practice doing that. Let's take this rectangular gate as an example. We know its width, we know the upstream depth, and the opening. In this case, the channel width is different from the gate width. And so now note that the canal may be 4.3 meters wide, but the gate is only 1.5 meters wide. So be careful that the V, the width that you choose in that underflow equation, is the width of the gate.
In this example, we have a 4.3 meter wide canal where there's an upstream depth of 2.7 meters of water behind a gate, and a 1.5 meter wide gate. That's the width of the gate, the width of the channel both, is opened 45 centimeters. After contracting, the downstream depth is 27.5 centimeters. So here we've got a channel, there's a gate, and the water depth Y1 upstream of the gate is 2.7 meters. The gate opening is 45 centimeters or 0.45 meters, and then the water contracts down, and the depth after contraction is 0.275 meters. And the question here is what's the flow rate? We've got a couple of different calculations we're going to have to do. First of all, the coefficient of contraction, of course, is the ratio of the downstream depth Y2 to the opening height of the gate, which in our text unfortunately has the variable of W. So we'll first do that. We've got 0.275, which is the contracted depth of water, and 0.45, which is the height of the gate. And with that, the coefficient of contraction 275, 0.45 divided 0.6111 is the ratio. Next we find the coefficient of discharge, and the formula for that is the coefficient of contraction and the square root of the upstream depth plus the upstream depth and the downstream depth. So 0.6111, the upstream depth of 2.7 meters, 2.7 meters plus 0.275 meters. Okay, so the coefficient of discharge, 0.6111, 2.7, 2.7, 0.275. .5822 is the coefficient of discharge. So now we can put all of that into the gate equation. Q is C sub D, B, W, square root of 2G Y1, and that is 0.5822. The width of the channel is 1.5 meters. The gate height opening is 0.45 meters. Square root of 2 times 9.81 meters per second squared. And the upstream depth of 2.7 meters. Doing the calculations. Oof, my battery just died. Did you hear that? Battery just died. I will fire up the backup HP. Okay, so 0.5822, 1.5, 0.45, 2, 9.81, 2.7, square root, times, and the flow rate is 2.86 cubic meters per second. And so that's our final answer for this example. So the flow rate through the gate
is 2.86 cubic meters per second.
Because gates often induce supercritical flow underneath them, because the opening is smaller than the critical depth, then one of the important considerations that we have in gates is ensuring that the hydraulic jump that can form after a gate doesn't drown the gate itself. And so if we want to prevent drowning of the hydraulic jump, then there are some things we can do to control how high the gate is opened, or the height of the headwater that we allow to form. So some of the procedures that we have to consider, first of all, is find out what the normal depth is going to be downstream in the channel, so that we know the capacity of the tailwater, and we should calculate the critical depth. We'll be going through these steps in just a moment with an example, but after finding the normal depth, finding the critical depth to find out if the channel slope is mild or if it is steep. In other words, if the critical conditions that come out of the gate are going to continue, or if we can expect a jump. The next part is finding the maximum gate opening. That's going to be the opening that is equal to the sequent of the normal depth. And if it's open any wider than that, then the hydraulic jump is going to approach the gate and the jump will drown the gate. If it's open smaller than that, then it'll run away from the gate. And so this opening, this maximum gate opening that prevents drowning, is what we previously referred to as the ideal hydraulic jump, where the hydraulic jump capacity curve is right on top of the tailwater capacity curve. So here's the equation we use for calculating the sequent depth in a hydraulic jump. And what we're saying is that Y1 is going to be the depth after contraction. So we're going to open the gate only as much as the water after it contracts will be equal to Y1, where Y2 is the normal depth downstream. So if we have Y2 is the normal depth, the critical depth we've calculated in step 2, and we want to find out what is the depth after contraction that's going to cause that perfect hydraulic jump, where the tailwater curve and the hydraulic jump curve overlap. And just again, if the gate is closed more than that, the velocity will be faster, and so that will cause the hydraulic jump to run away. If the gate is closed smaller, that's going to cause more cooling upstream, and so the velocity will increase. But if it's open more than that, then the jump will be drowned.
Dr. Wade,
Mm-hmm.
a sequence of the normal depth, that just means like downstream to the normal depth, at depth, or
If we have a momentum depth diagram, so this is the momentum function M, and this is the depth Y, we're going to find out the normal depth downstream. It's going to be some normal depth based on Manning's equation. So if we go over to our momentum depth diagram and then we go down, this is the normal depth for the conditions that we have in our channel, based on the end value, the slope, the channel geometry, Q. This is going to be some supercritical depth that is the sequent or the conjugate. And so it's the depth that has the same amount of momentum function. It's the alternate depth that, well, I don't want to say alternate depth, because the alternate depth is the one that has the same amount of specific energy. It's the sequent or the conjugate depth.
Dr. Wade,
Mm-hmm.
when you say drown the gate, what do you mean by that exactly?
It's the behavior we saw in the lab when we made the slope really shallow. We could move the jump back and forth by how steep the channel was, but when we made it very shallow, the hydraulic jump got closer to the gate, and then eventually, instead of here's the gate, and it's flowing for a second, there's the hydraulic jump, and it goes up. So this would be an instance where it has run away from the gate, but it can get a little bit closer, and then jump up, if it drowns the gate, that means that the water is like this, and the hydraulic jump is still there, but it's actually submerged underwater, so we don't see it.
So why is that bad exactly?
Well, because it's causing unstable conditions where it may make it difficult for us to quantify the flow rate that's actually going through the channel. We don't get to see the hydraulic jump, and so that's a big negative. I guess the main reason why we wouldn't want it to be drowned is that means that the channel doesn't have as much capacity as we need it to. I'll have to think about that some more. So here's the illustration of the ideal case, and it's just showing that as soon as the water finishes contracting, it jumps. The jump occurs. And if we close the gate more, that's going to push the jump further to the right. And if we open the gate more, that's going to cause the jump to run into the gate, and then it'll drown the jump will be drowned. All right, so here's the example where what we want to do is find out how much the gate can be opened. And the way that we do that, it's in sort of a little bit of an iterative process. Remember, from the previous slide, first calculate the normal depth of the downstream channel. And so we have everything we need to calculate that. We know the slope, the roughness, the flow rate. We know the channel width. And so we'll find the normal depth using Manning's equation. And then in the second step, find the critical depth. And the critical depth, since this is rectangular, can be found with the equation y sub c is flow per unit width squared divided by g to the 1/3 power. So that's the second step. And then the maximum gate opening we calculate, excuse me, by setting the depth at 1 before the jump equal to the, the hydraulic jump equation we had here. We're setting the y2 equal to the normal depth and then solving for y1. And that tells us the depth before the jump. And we'll assume the coefficient of contraction is 0.6, and so then that's how you find y sub g, because there will be some coefficient of contraction that relates y sub g and the y before the jump.
So now we've got the second gate example. This one's a little bit more complex, because we have both a gate and a hydraulic jump that we're going to be doing calculations on. So let's get a sketch of the situation and enter in some of the information that we know. Here's a gate, and there's water pooling upstream of the gate. The water coming out contracts a bit, and then it goes through a hydraulic jump and up to a depth. And so this depth after the jump, and there's the depth before the jump. There's the gate opening, W, and then there's this upstream depth, Y1. What we know is that the canal width is 5 meters wide, and that the gate is carrying 25 cubic meters per second. The coefficient of contraction is 0.60, and that's the ratio of the water depth after it contracts to the gate opening. And so how much can the gate open without drowning the hydraulic jump? Okay, so our first step here is we're going to need to find what is the normal depth. And the Manning's equation is what we can use to calculate the normal depth, where we're entering in the channel geometry, the material type, and the slope, the flow rate. In this case, we know that the flow rate is 25 cubic meters per second, the N value of the materials that the channel is made out of, 0.02. That's given in the problem statement there at the top. And the channel is 5 meters wide and rectangular, and so the area is going to be 5 times the depth. And what we're solving for here is the normal depth. And the wetted perimeter is 5 plus 2 times the normal depth. Again, we kind of lucked out that it's a rectangular channel. And the slope in this channel is 0.003. Okay, so we put that into our solver, find the depth. The normal depth is 1.78 meters. Now remember, downstream of a hydraulic jump, the water is eventually going to reestablish whatever the normal depth is. If there aren't any more interruptions, any more features in the way, it'll just eventually get back up to the normal depth. And so what we're trying to find out is if we open the gate less than this ideal amount, then that'll cause the water to run downstream, because there will have to be some gradually varying flow before the upstream sequent depth is deep enough to match up to the normal depth. But if we open up the gate too much, then that's going to cause the water to run towards the gate. And the reason for that is that the sequent depth after the hydraulic jump, the downstream sequent depth, is going to be lower than the normal depth, meaning that the channel capacity is going to be less than the hydraulic jump capacity, so it will drown the jump. Second step here is to find the critical depth. And we know in a rectangular channel the critical depth can be calculated relatively easy. So we've got 5 meters squared per second, since it's 25 cubic meters per second and a 5 meter wide channel. And so that the critical depth is 1.366 meters. So since Yn is greater than Yc, subcritical conditions downstream of gate. That means there is going to be a hydraulic jump. A jump is going to occur. We've got a mild slope here. So the maximum gate opening corresponds to the opening that produces, after contraction, the sequent to the normal depth. So gate opened such that after contraction the water depth is equal to the sequent of the normal depth. So we're doing the hydraulic jump calculation, and what we're doing is we're saying that the downstream depth after the jump is equal to the normal depth. And so we want to find out what is the upstream depth of that. So what's the Y before the jump? That after we scale it up for contraction will tell us how widely we can open up the gate, how tall it can be. Alright, so we're going to be finding Y before jump, and that is the Y after jump divided by 2 minus 1 plus the square root of 1 plus 8, and then the Froude number. One way to find the Froude number is YC to Y after cubed. Well, actually, no, that's not the Froude number, but we can use this as a substitute for it in the hydraulic jump equation. Okay, So this is just one form of the hydraulic jump equation, and if we substitute in the depth after the jump, so we're saying it's going to be the normal depth of 1.78 meters divided by 2. And the ratio of those two depths, 1.366 meters, and 1.78 is the depth after the jump cubed, then gives us a depth of 1.022 meters. So y before the jump is 1.022 meters. Remember, in hydraulic jumps, there's the same momentum before the jump as there is after the jump. And so these two depths are sort of perfect pairs of one another, where they're sequent depths. And we say that we know eventually the water downstream of the jump is going to set up at the normal depth. And so we're setting the depth after the jump equal to the normal depth because that is the as close as we can get to the gate. We open the gate wide, the jump comes nearer the gate. So the sequent of the normal depth is this y before the jump, and we've just found that. And so now we're going to calculate, if we scale that down for contraction, how much the gate can be opened. So for this y before of 0.022, and we know that c sub c is y before to the depth of the gate w, and that is equal to 0.60. Then w, which is the gate opening, is going to be y before divided by coefficient of contraction. So 1.022 meters of depth divided by 0.60. So 1.703 is the maximum that we can open up the gate. If we open the gate less than this, then the jump will run away from the gate. If it's a small opening, then it's going to jump up to a higher depth, and so it'll be further away from the gate. But if we open up the gate more than this, then the jump is going to drown because the sequent depth will be less than the normal depth. Okay, so there's another part of this example where it's asking us to calculate the oh, my screen just went blank. The depth behind the gate. And so this is a gate problem. This is the gate part of this example. And so depth behind gate for the flow rate is c sub d times b times the gate opening height w, the square root of 2g y1, and we know that the coefficient of contraction is 0.60. Then the flow rate is going to be coefficient of contraction times the square root of y1 plus y2, b w square root of 2g y1. So we know that the flow rate is 25 cubic meters per second. The coefficient of contraction is 0.60. We don't know the depth of the water upstream of the gate, but we do know that after it has contracted, the water depth is calculated this previously, 1.022. And the width of the channel is 5 meters. The gate opening is 1.703 meters. And the square root of 2 times 9.81 times y1. So y1's in a couple of different places here. Put it into the solver. And if you don't have a calculator that'll do solver, you can of course put this equation into Excel and play around with different values of y1 until whatever value of y1 gives you the flow rate of 25 cubic meters per second. When we do that, we get that the depth is 1.883 meters, and so this is the depth upstream of the gate. So let's just summarize 1.883. 1.883 is how high the water was pooling upstream of the gate. The water goes through the gate, which is height W, and W is 1.703 meters. It contracts until it gets this depth before the jump, which is 1.022 meters. And the depth after the jump, the normal depth, was 1.78 meters. If the gate is open more than that, it's going to cause the hydraulic jump to move to the left, and it will drown because the opening the gate higher draws the jump nearer to the gate, and the capacity of the channel is less than the capacity of the gate. But if we close the gate more, then that will cause the jump to run away, and the reason why is that the water would need to gradually vary prior to the jump so that its before jump depth would be bigger. So that is the conclusion of gate example number 2.
In a previous lecture, we took a look at how the downstream channel, the tailwater, how the normal depth of that can affect the location of a hydraulic jump. The fact is that the gate itself can also play a role in determining where the hydraulic jump sets up. And so let's take a look at this figure again, this figure which is picturing the downstream jump, as we called it previously. So in the case of a downstream jump, if we are closing the gate pretty close, if the gate is closed more than the normal depth downstream would support the jump immediately, then that makes the water to run away from the gate. In other words, you can see that we've got the gate closed relatively tightly here, which is going to lead the water to be very supercritical as it comes out of here. This is the location of the jump where it would naturally jump up to if it jumped immediately. So the sequent of this very shallow depth here would be a relatively deep hydraulic jump. But on the other hand, since our channel downstream can only support this normal depth Y2, what you'll notice is that in this instance, since the gate is closed so much, the jump has to run quite a bit before it finally gradually varies to a depth here at Y'2 that will have its sequent depth be the actual downstream normal depth. And so what we see here is that the gate being closed made the jump run away. On the other hand, an upstream jump can form not only just if the tailwater condition is a relatively shallow slope or a high roughness, whatever it is that's making this depth Y2 great, but rather if we open up the gate, then that can cause the water to draw nearer towards the gate itself. It causes the jump to run towards the gate, and it can drown the gate itself. Whereas if we had closed the gate more, you'll notice that in this case the gate opening is large. If we had closed it more, then that would have caused the sequent of that jump to match up to the water surface. And so you can see from both of these depictions how it's really a continuous iterative thing that the downstream channel conditions and also the gate opening conditions cause affect the location of the hydraulic jump itself. So if we just run back to a couple of announcements here to remind ourselves what is going on, please don't forget to take that online quiz. The deadline for that is Saturday the 12th at 11:30 p.m. And there's only one question there, and I think 20 minutes should be plenty of time. Also, homework 11, chapter 13, those problems, and then also the lab demo question that I gave you during hydraulic jump day. That'll be due on Tuesday the 15th.